presentation for this SNAM Webinar 3, and we have been doing a series of technical webinars individually as well as in conjunction with some Foundry fraternity platforms. And this is our third webinar, and we'll be discussing about the most important T's, or the 3 important T's in ductile iron. So I'm maintaining the suspense, and I'll open the suspense in the second or third slide, and I'll tell you what are those T's, important T's, and hope everyone are safe and fine. So from being a supplier to cast iron foundry, we are happy that in India we are back into workforce. Like we are trying to achieve the maximum production capacity, and hope this keeps continuing. And let us all be cautious, and let us be attentive in our work. And before starting or before getting into the presentations, I wanted to give you some important facts about foundry industry and metal casting industry. So let us know about some important facts from our past. The first cupola ever in the metal casting industry was established and installed in England, and it was in the year 1794. And the first tumbling mill. So we know tumbling mill, where the castings pass after the shakeout for removal of sand, and it is just before the fettling. So the first tumbling mill for casting cleaning, small castings cleaning, was established in the year 1880, and the first ever compactability test for a green sand. So most of us are green sand foundries. So the first ever compactability test and the methylene blue test, which we do for the green sand additives and the binders. So it was done in the year 1960. In the same period, 1960s only, the high pressure molding concept was developed, and the first disamatic machine, one of the common and the prevalent disamatic machine, or the high pressure molding line available in today's foundries, was established in the year 1964 to 1965. And we all very well know about the cold box process, which is a core making process, and there are a lot of highly developed and highly automated machines available today in the market and in foundries. The first cold box process was introduced in the year 1968, and we know about the developed form of ductile iron, like Ostemper ductile iron, a heat treated form of ductile iron, where you have got increased tensile strength as well as increased elongation properties when compared to the conventional as cast ductile iron. So the first ductile iron, the first ADI, Ostemper ductile iron component, was produced in the year 1972. And we all know that there is one other form of iron which is booming now, like the compacted graphite iron, which we talk of, an intermediate family of cast iron, which falls between gray cast iron and ductile iron. Compacted graphite iron, which has got a high strength and increased elongation than gray cast iron, was first developed and first tried in the year 1976. So these are some of the facts from our past and from our timelines of metal casting industries, and hope we also put in lot of efforts to come up with new technologies, and we also become a part of inventions and developments that happen in the metal casting industry. So coming to today's presentation, so we'll be talking about ductile iron today. So our ductile iron metal has got graphite, where carbon is present in the form of graphite. The free carbon is present in the form of spheroids or nodules, we call in the graphite, in small shapes. Small is small is an adjective, so it is very relative to the requirements and the casting dimensions, and evenly distributed throughout the matrix. So we use the word evenly, means it is required as per the casting section thickness. So we cannot expect to have a 300 nodal count in a 80 or 100 mm section thickness, but based on the section thickness, the nodal count varies and the nodularity slightly gets adjusted. So talking of a complete ductile iron casting, so specific to its own property, like ductile iron has got a property of section sensitivity in nodal count particularly. So to get a uniform ductile iron, we need a uniform microstructure, and to obtain uniform microstructure, there are a lot of chemical reactions and processes which we follow or which happens in the production process, which is to be controlled. So unless we don't control, we'll not end up in getting a uniform microstructure that will end up in giving you a varying properties. So to control the chemical reactions and processes, we should understand some of the major influencing factors in our foundry, which we have direct control over, which we can control or which we can monitor and measure and control. So today we'll be discussing about those three important parameters. The first T is time, the second T is temperature, and the third T is trace elements. So we'll be going in the sequence. The first T will be talking about time. So initial slides will be about the time and how time is being measured and where all time is to be measured and what is the impact of time over producing good ductile iron castings. And second will be temperature, the same way, where all temperature is being measured right now and where all it is to be measured and how it has got impact over a good ductile iron castings. And the third is about trace elements. So we'll be talking about some of the elements which have got impact over the microstructure and directly again impact over the properties of ductile iron which we produce. So this is a typical example. So this is a extended or an elaborate form of magnesium recovery calculation. This is prescribed in Soral Metal Handbook. So which talks about the nodalizer required. So if it is a ferrosilicon magnesium based nodalizer, what the amount of nodalizer by weight required to achieve the final required magnesium, residual magnesium. So when you look at this formula, you have got two important parameters on the top, like the time and the temperature. The small t talks about the time, the bigger T, the capital T talks about the temperature. Because these two ends or results in giving you good residual magnesium as well as or enough residual magnesium to produce good microstructure. So the final properties are going to depend over the microstructure, which is again decided by the time, temperature, and the chemistry. So in chemistry, we'll be talking about the elements which are we already know that the elements which are going to be good and which are going to be favorable to produce ductile iron. So today we'll be talking about some elements which are deleterious or which we do not want, or some which misses our overview or which misses our scrutiny, which entering the ductile iron process and hinders the ductile iron production and producing good castings. So this is a typical example how time and temperature is more important when we talk about achieving a good recovery. So getting into the first T, time. So time is one of the key variables in ductile iron processing. We very well know about the pouring time. So anything you talk of any ductile iron foundry, even the within peer groups we talk or we evaluate a foundry or we talk about or we name a foundry as being good means, so if they have a very good control over pouring time. So the first thing when we ask a foundryman from ductile iron casting industry is what is your pouring time? Do you pour 8 minutes or 10 minutes or 12 minutes? What is your last box pouring time? So we always refer to the pouring time as one of the most important parameters. So we'll be going in detail about how different locations time is important and how different locations time measurement is important. So most of the chemical reactions and its efficiency are time driven. Say for example, for magnesium to react, so magnesium plus liquid metal has got a reaction which is a chemical reaction. So how quick the reaction happens is decided by how quick you tap your liquid metal over magnesium, or retention of magnesium in your liquid metal is dependent on two variables. One about the amount of magnesium, number two is to the time in which you have magnesium in your liquid metal. So retaining magnesium in a liquid metal is one way the chemical reaction, the other way is time dependent. So this way most of the reactions happening in the foundry to produce ductile iron are time and temperature dependent. Say for example, slag. So when we hold the liquid metal in a furnace for a longer time, we start getting more amount of slag. That is the furnace lining getting eroded. So it is a temperature phenomena as well as time phenomena. So so this way time plays a major important role in ductile iron production. So it is very important for us to understand how the time factor has an effect on all the process parameters what we measure and process measurables, process outputs what we expect, and variation in the time or letting the time not being measured also plays a major role, and it can be a setback in analyzing a casting defect, where we always think that we are following all the practices on the right track. So I have listed down from the furnace till the last pouring, where and where all the time is going to be measured. Time is to be measured and how important it is. So the furnace melting time. So the time measured or time taken from the solid charge till the liquid metal is generally measured as furnace melting time. So this has got a direct relationship with the amount of metal you have to be melted and the frequency or the power input you use for melting. And again, it depends on the charge material you use. So when we talk of charge material, we have got three different kinds of charge material generally being added. Three or four kinds, like pig iron, CRCA scrap or steel scrap, it is called, and the foundry returns, which is runners and risers from the foundries, and the borings. So when we look at all these four materials, pig iron has got a comparatively lower melting point because pig iron has got high carbon, and in the iron carbon alloy system, it is comparatively fast melting because it has got carbon. And returns, we know our pouring temperature, we know our liquidus temperature for our material which we cast. So returns has got the comparatively lowest melting temperature. Borings are nothing but returns again in a different form. So borings have got similar melting point. Steel, which has got a higher melting point, because when you look into the iron carbon system diagram, like equilibrium diagram, steel has got a very high melting point than conventional cast iron. So this way, when you tend to play with our charge mix, our furnace melting time increases. So this has, to some extent, has an impact on the nucleation potential, because the time we take for melting involves a diffusion process where carbon is we add carburizer for during melting to pick up the carbon. So when the time taken for melting is increased, that means we tend to add more steel. So that means then there is a requirement of more carbon to be diffusing into the liquid metal, because steel has got almost nil carbon. So we need to make it up to, say, if we are producing a ductile iron, not less than 3.2, 3.3 carbon. So we need to keep adding more carburizer. So the time taken for diffusion will be more. So more carbon has to go into your liquid solution, because steel is going to give you a low carbon rich liquid metal. So this way, the diffusion process is going to be a bit difficult, tricky, but it is not so significant, but it is also to be measured. And next comes the furnace holding. So after you have completed your melt, that means your liquid metal is ready to get tapped, you then go into the phase called holding. So most of the people or most of the foundries do not hold the metal, because as they are very well aware that holding is going to increase their energy cost, and holding is also going to reduce their nucleation potential, and it may lead to different various defects. It can be a slag related defect, more amount of slag getting generated, or it can be a structural defect which talks about like less of nucleation potential, and then leading to demanding more inoculation, and maybe leading to remote location shrinkages. Like in thick sections, you can get a lot of shrinkage. So it's talking about the furnace holding time. What happens in this furnace holding time is, that means you are already reached the tapping temperature. It can be XYZ. It can be 1520, 1540, 1560. And when you reach the tapping temperature, you're holding the metal at the tapping temperature for a longer time. What happens is, in that given tapping temperature, that means it is just above, it is already superheated, and you're holding it for a longer time. Your furnace metal by itself has got its own some potency. So we have got graphite in our returns. So graphite means graphite is produced out of a nuclei which is already produced in the previous melt. So your returns will give you some nuclei. You have added carburizer, you have added ferrosilicon to it. So these elements give you some nuclei, and your pig iron has got some carbon, that will give you some nuclei, and your steel which has taken carbon from your carburizer will give you some nuclei. So there are already some amount of nuclei available in your liquid metal. When your holding time is increasing, you start losing this nuclei. Why do nuclei go? Why do all these nuclei go out of liquid metal? There is a stability temperature for all the nuclei bound. So when you're trying to increase the temperature and when you're trying to hold at the same temperature for a longer time, your nucleus starts getting disintegrated. It is like nuclei tends to form and tends to get stabilized, because after tapping there is no melting, so the temperature keeps decreasing. So there is a particular time and temperature where your nuclei gets formed and then becomes stabilized. It is called as threshold level or stability time and temperature. So when you don't let the temperature to keep coming down, you start losing the nuclei which is about to form or which is already present in the liquid metal. So furnace holding time matters. And next question will be, why should the foundrymen hold the liquid metal in furnace? It can be because of various reasons. It can be based on their foundry layout, where they have to do two different pouring lines, or there can be a molding line breakdown, or it can be other reasons why the chemistry adjustments could take a lot of time. So care to be taken that, and there should be a measure that how long the metal is being held every tapping, such that you can have a control or you can relate it to any of the casting defects which is coming up, so you can take corrective actions. That means you should keep your mold ready, tap the metal and pour, or you should try to achieve the chemical conversion as quick as possible, such that you don't hold the liquid metal for a longer time, because all these things will have an effect on the final casting property, or all these holding time will start demanding extra additives. And next comes about furnace holding time between two consecutive tappings. So say for example, we have got a 1-ton furnace and you have got a 500 kg ladle, and or let us consider 2-ton furnace which has got a 500 kg ladle. So technically we'll be having 3 or 4 tappings to empty the furnace. So the time between the first tapping and the fourth tapping, or first tapping and third tapping, should be monitored. So what happens if there are 2 or 3 different lines, and there can be a slight increase in the tapping time? Maybe first tapping, every tapping should be say 20-30 minutes. Say you tap and then you pour, your tapping time maybe 20-30 seconds or maximum 1 minute, and then you pour up to 10 minutes. So your tap to tap time will be average of 10 to 15 minutes. Say if some instances it can become 15 minutes, or some instances it can become 20 minutes or 30 minutes because of some molding line breakdown. So what happens is, by default, the first tapping and the third tapping is going to be slightly different, because the metal is not going to be the same. As we had discussed previously, holding of liquid metal at a higher temperature is going to start losing its potency. So furnace holding by itself is going to give you low nucleation. And if between two different tappings there are from the same furnace, if it is going to be a different timing, then the first metal is going to behave differently for the inoculation or nodalizing treatment you do, and the third tapping or third metal is going to be responding differently to your inoculation and nodalization treatment. So we can expect a variation between first tapping and third tapping. So this is when people try to add extra additives or have a chemistry control, or try to alter their layout such that you cannot nullify the variation, you cannot nullify the loss, but you can have a control and measure over the loss. And furnace to treatment ladle tapping. So tapping plays a major role, and it is one of the difficult process being handled in foundries, where tapping and treatment has a lot of violence coming up. So during violence, the operator or the person who is tapping will not be able to view the ladle properly and tap it continuously, and so there can be a possibility of intermittent tapping. So when your tapping time is longer, that means you, instead of tapping a 500 kg metal in 30 seconds, you tap 500 kg metal in 40 seconds or 50 seconds. You're letting the entire nodalizer you have already added in the liquid metal, or you already added in the ladle, to react it to a lesser liquid metal weight. Say for example, if you are supposed to empty the or fill the ladle of 500 kg in 30 seconds, instead you have filled only 75% of the liquid metal. Say 75% of 500 kg is going to be 350 or 400 kg. So that means your for the 30 seconds, your entire alloy would have reacted to only 75% of your liquid metal. The balance 25% of the liquid metal which you are tapping extra, or which you are tapping it late, will just going to be stay on top, which just going to stay on top of the reacted metal, and it is going to be a diffusion process where magnesium is going to slowly come and mix by itself. And as there is no mixing happening after tapping, after furnace, and this top liquid metal which is going to go to your last box pouring will have a severe impact on your fading and nodularity and residual magnesium also. So this increased tapping time or uncontrolled tapping time or intermittent tapping happening in foundries will have an effect which generally is being overseen, telling that we have been doing the tapping like this for longer time, and this is the possible tapping time available, so we cannot do anything better than it. So it is always best to have the maximum metal over ferrosilicon, magnesium, or any nodulaser to get the maximum benefit out of it. As we know, magnesium is a highly reactive element. And reaction start time and end time. So this matters a lot. So when this is influenced by the previous time which we measure. So if we are able to see a particular alloy with X% magnesium is going to be violent, and based on the amount of magnesium present and the process we are going to carry out, say open ladle or closed ladle kind of. And when this time is, when your tapping time is going to vary and your reaction start timing is going to be very early and it will end very quickly, because you don't have enough liquid metal available to slowly or subdue the reaction time, or reaction can happen slowly. So the reaction start time and end time for a given alloy for a given process is influenced by your tapping time also. So every process, every parameter which I show here is interlinked to itself. So if you have a very high temperature and when you very slowly when you tap, your reaction is going to be different than your normal conditions. And the time of transfer between tapping and pouring. So this depends on your complete foundry layout, and all these things depends on how usefully we maximize the capacity of the treatment ladle and pouring ladle, such that you do a quick transfer, and your arrangements of ladles where your transfers are very closer and quicker and your pouring line is closer. So this can be a backlog where your pouring lanes are slightly longer from your melting platform or your transfer platform. So care to be taken that your arrangements are made such that your time between tapping and pouring is reduced or minimized. You cannot nullify, but there are technologies available. There are people who already do tapping. The same tapping treatment ladle is being used as pouring ladle, but that is again a foundry constraint where their number of boxes or their process does not suit it. So holding time in press pour. Same. This time we'll be talking about the time taken where the liquid metal is held in the press pour or any automatic pouring line, where liquid metal after coming from tapping and just before filling. So if the liquid metal, the treated ductile iron metal is held in the press pour for a longer time, what happens is you start getting lot of reaction products which is supposed to go into the mold and become good ductile iron. It will start reacting and start losing its potency. So as I had mentioned, all the reactions are time dependent, and when you leave your liquid metal, the treated liquid metal at the same temperature, or as the temperature keeps coming, your time keeps increasing, the reaction keeps happening, you don't get benefit out of it. So magnesium is going to react with oxygen and sulfur, it is going to lose by itself. So our target should be, let before it loses its maximum potency, let us complete our casting. So let us fill all the molds available before all these losses happen. So if any of the delay happens before filling of the mold, so you are losing your potency of your process. That means your nodalization treatment process would have given some efficiency, but you are losing it because we are delaying it during the process. So inoculation to pouring time. So inoculation is a process which adds nuclei to a liquid metal and which is again time dependent. So the time in which the nuclei forms and the nuclei is sustained for a longer time is dependent on the time taken after addition. So if, for example, you add your inoculant at the latest stage, say after first transfer and second transfer, you do inoculation, or you do an inoculation closer to the furnace and your transfer is 2 times, and then after 3 minutes or 4 minutes, you start pouring into the mold. So your entire 3 minutes of inoculated metal and the potency which is developed in that entire 3 minutes is lost. So there is a time, there is a dwell time where the inoculant has to react and start giving nuclei. That will happen in microseconds. And if we delay it any further or any later, the extra time we take before pouring after inoculation is a loss to us. So foundries should have a control and have a measure and should have a practice of pouring it immediately or very closer after inoculation. So casting pouring time. Next comes the pouring time. So from the first mold till the last mold, this is being measured as the efficiency of a foundry. So how quickly you can fill a casting, or how quickly you can fill a mold, and how long you will be able to pour with the treated liquid metal without losing its potency, and uh, getting good castings out of it is a challenge, and that is weighing, and that depends on the foundry capacity and foundry to foundry. It depends on various parameters like your method of pouring, your ladle capacity, your casting type, and the bunch weight of the casting, and the criticality of the casting. So, and the temperature control over liquid metal. So there is no guarantee that you need not compare a 8-minute foundry and a 10-minute pouring foundry, because 8-minute foundry would be pouring a different type of casting, or they'll be having a different pouring ladle, and they'll be pouring in a different sequence, and a 10-minute foundry will be following a different process and a different type of casting. So it is a self evaluation, not a comparison directly telling that my foundry is, say, foundry A is pouring 10 minutes and foundry B is not able to pour 10 minutes, but they are able to pour only 8 minutes. So it should be foundry B self-assessing themselves that last month I was able to pour in 8 minutes the same casting, and this month what improvement in my process can I do such that I can extend my pouring to 30 seconds instead of 8 minutes. Let me pour 8 minutes 30 seconds, rather than comparing a foundry A which is pouring in 10 minutes with a different setup. So the time plays a major role, because as we had seen previously, all the chemical reactions are time dependent. And casting filling time, so this is talks about the mold filling time. So in case if there is a auto pour system, and which is generally controlled by pneumatic or some mechanical operations, the filling time of a mold is going to be constant. So if the filling time of mold is going to be averagely constant, you're going to get uniform properties, uniform cooling time in the castings, and uniform properties throughout the castings. And if it is going to be manual pouring, and if the pouring rate is going to change between the single heat, and that will have a direct impact on the cooling rate of the casting, it can affect your mechanical properties or microstructure also. We might not be able to identify, or we don't have a track of every single mold pouring time. Say for example, if you are supposed to pour fill a mold in 10 seconds or 20 seconds, a bigger mold in 20 seconds, and in a heat you might have to pour 10 boxes or 20 boxes. For every mold we do not have a time record, unless it is a automatic pouring line. We do not have much of a time record for every pouring. So we should be able to pour it at a constant rate, average rate. And sampling time, so people used to take sample after pouring the last box, or closer to the pouring the last box. So there can be a standard practice being available made in the foundry, where you tend to take the sample at the given time every time, such that you can start comparing one heat over the other. And casting knockout time has got a surface impact on the castings, where your surface hardness can increase, or your residual stresses in the castings can increase when you knock it out at a early time. Also, this knockout time has got an impact on your entire foundry cycle. As foundrymen, we know that very well. So these are places from furnace till last knockout, where time is to be measured, and time plays an important role in influencing all the uh, output of getting a good casting. So this is a typical example of a foundry data which we have taken in our experience, where you see when the tapping rate, that is kgs per second, varies, and if you tap at a faster rate, you're able, for the same given rate and grade of ferrosilicon magnesium and similar addition rate, you're able to get better residual magnesium at the last minute with a similar tapping temperature. So tapping rate matters a lot, as I discussed previously. And we know very well that nodularity and nodule count fading with time. Nodularity is to some extent decided, or it is very much dependent on the residual magnesium and the section sensitivity and the section thickness of the casting, and cooling rate also. And as all these things are related against over time, so time plays a major role. So there is a specific time available, and control over time is to be maintained. And nodule count is again an effect of nucleation and the amount of nuclei present, which is again inherently present in the liquid metal, also being added from your inoculation addition. So that is again time dependent, its efficiency. So these two are major important parameters, microstructural constituents, which decide your uniform casting properties. Nodularity, nodule count, and other microstructure ingredients or constituents vary with time when there is variation in the time being measured in individual process of production. So with this, we come to end of discussing over time. So this is again a graphical representation or microstructure representation of how fading happens with time. So increasing holding or extended pouring time after treatment decreases the effect of nodulization, which leads to vermicular graphite, which is not desirable, or not accepted in ductile iron production. So we'll be going into the second T, which is temperature. So temperature is again one of the key variables. As I mentioned, temperature which is being measured at two different levels, like tapping, pouring. So these are places where people generally measure temperature. So temperature and time are two important driving factors which take place in all the chemical reactions and processes happening in foundries. So we'll be going into details about how and where temperature is being measured and to be measured. So furnace holding temperature, that means after the metal is ready and before tapping. So as we had mentioned, the temperature at which we hold the metal matters a lot. So we generally hold the metal at close to melting temperature or slightly below the melting temperature. So for tapping temperature maybe. So this holding temperature again has an impact on the amount of nuclei present, and when you try to hold the metal for a longer time at a very high temperature than required, so like superheat, which we call, superheat is the amount of temperature above the melting point of the alloy. Say for example, if a ductile iron's melting point is 1150 degrees Celsius and you hold that metal at about 1520, 1530, which is the tapping temperature of the liquid metal. So you've got a superheat of almost like 370 degrees Celsius. And if you hold that temperature of the liquid metal for a longer time at 370 degrees Celsius extra for a longer time, you will start losing the nucleation available, because nuclei tends to form only after or only below the liquidus temperature. That means the melting point of the alloy. So that means you are keeping very high temperature above the nuclei formation, and you start destroying the nuclei when you hold at a very high temperature. And next comes the furnace tapping temperature, which is generally being measured. And there are some shortcomings available in foundries where, I mean, there are consecutive happening, and when the metal level keeps going down in the liquid, in the furnace, melting furnace, people find it very difficult to measure the temperature. And they with their experience, they visually analyze the liquid metal's color, and then they tell it can be close to 1500, 1520. But every degree Celsius of temperature has got an impact on your entire process of ductile iron production, because temperature has got an effect on your ferrosilicon magnesium's dissolution and the recovery of the liquid metal. So recovery of magnesium from your ferrosilicon magnesium, your temperature loss is going to be determined at the temperature you which tap. So your a small assumption or a miscalculation or a wrong measurement or not measuring of tapping temperature is going to give you no clue about what is going to come in the future. Maybe there can be a loss in, or there can be a defect coming up in the particular heat pouring, where you do not have a reference tapping temperature to stratify or to reason out why the defect would have come up. So tapping temperature plays a major role, and measuring the tapping temperature plays a role, and controlling or having a close control over a given range or minimizing the range of tapping temperature plays a major role. And ladle preheating temperature, and we are being advised by foundrymen and experts to maintain a very high temperature of ladle, such that you avoid or you reduce your tapping temperature, as such that your temperature loss during treatment or temperature loss during transfer is being taken care. But there is a catch. When we tend to preheat the ladle to a greater extent, what happens is there will always be some slag or some residue liquid metal left over, which is stuck to the liquid, which is stuck to the walls of the ladle. And when you preheat it to the maximum level, you start getting reactive products. You start melting the material which is stuck to the wall of the ladle. So material which is stuck to the wall of the ladle are generally slag or oxide or sulfides generally. So when you preheat to a very high extent, these sulfides start coming out of from the slag or whatever material which is stuck to the ladle. So you suddenly get a sulfur increase in your liquid metal, and you will be surprised to see how the sulfur increased from uh, liquid metal from furnace to the final pouring. Because this sulfur, which is not accounted or which is not measured, can get into the liquid metal again because of this very high ladle preheating temperature, or very high ladle preheating temperature. So because of this, your increase in sulfur can be small or it can be localized, which can affect your magnesium recovery and your entire properties. So care to be taken that we do not preheat the ladle to a very high extent. Also, the cleanliness of the ladle plays a major role, because if there are more slag stuck to the ladle, then foundries tend to preheat the ladle to a greater extent. And when we tend to preheat the ladle to the greater extent, the slag starts getting liquefied, and you don't eliminate the slag, you liquefy the slag and you let it enter into the next metal which is going to come, the cleaner metal. So slag is nothing but oxides and sulfides, as we know. And when oxides and sulfides come into the liquid metal, it is going to be dangerous. So care to be taken that we ensure there is no slag built up, or there is almost less slag available in your treatment ladle or transfer ladle, and we do not preheat it to a very high temperature. And the next comes the temperature after transfer of metal from treatment to pouring. So here it is about the loss in temperature, or this is the time where we add our inoculant during transfer, or transfer from tapping to a pouring ladle, or transfer from tapping to a press pour or an automatic pouring system. So this is the time generally people used to add inoculant. So the temperature at which inoculant is being added, the temperature at which the transfer is happening, has got an impact on the nuclei which is about to come into the liquid metal and its stability also. So we need to maintain at the minimum required temperature, such that you don't get any filling defects or pouring defects. So that is the amount of temperature required enough or sufficient enough for casting. So anything above that is going to kill all the special requirements or special additives which you have already added to the liquid metal to obtain good ductile iron production, ductile iron castings. Then comes the holding temperature at press pour. As we have seen, the holding temperature again, when the holding temperature is going to be very high, your property loss in the liquid metal is going to be very high. And average the first and last box or last mold pouring temperature. And when your pouring temperature is going to be drastically varying between the first mold and the last mold, and your casting is going to cool in different way, and as the casting cools in a different way, your cooling rate has got a different effect on your microstructure and thereby the properties of the ductile iron, the castings. So the first box casting and last box casting can be slightly different because of the temperature at which we fill. And as we have seen, the mold filling temperature, the average mold filling temperature should be technically constant throughout the entire process. And the knockout temperature, which is directly related to this residual stress, also the phase transformation happening. So if you knock out the casting above 750 degrees Celsius, as we know that the eutectoid transformation is going to happen at 723 degrees Celsius, which determines your perlite content or the coarse or fine perlite which is going to come. So when you knock it out very early, there is a tendency that your fine perlite, your coarse perlite can become fine perlite also. So what happens when your holding temperature or melting temperature is high? These are the negative consequences. We know very well that refractoriness of the lining material can become weak, and you start observing the wear of the refractory lining. And there's a catch: when the refractory lining in the furnace or in the ladle gets eroded, it is just silica, SiO2. And as the temperature is going to be very high, this SiO2 gets reduced into Si and oxygen. This oxygen, in the presence of carbon, reacts with carbon and forms carbon monoxide or carbon dioxide. The problem is this carbon monoxide and carbon dioxide is a very strong reducing agent. So it can lead to chain reactions happening in the liquid metal. So you start to get more amount of slag. This is the reason why furnace erosion leads to slag. And furnace erosion is because of very high temperature, melting as well as pouring or holding. So longer melting time means more energy consumption and increased cost. And working environment can be very hot, so it will become very difficult for the operators to handle, and your entire handling a ladle starts becoming weak. And as we know, it can lead to lower nucleation potential. That means it can lead to either thin section carbides or demand for more nuclei, or all nuclei deficient related defects in the castings can come. Low nodule count, increase in chilling tendency, increased hot spots, remote location, microporosities or micro shrinkages can come. So this is the effect of temperature on oxygen content. So when you keep increasing your temperature, there is a high tendency that oxygen can get retained in your liquid metal for a longer time. And because of this high oxygen content, you start losing your magnesium, your all the oxide forming elements in the form of oxides. And it should be uh, lower or to the adequate level. So it is better to tap at the lowest possible temperature, such that your oxygen influx or oxygen retention in your liquid metal is compensated or maintained, such that your amount of oxides which is going to be formed or loss of magnesium due to oxidation can be controlled. And when the treatment or tapping temperature is going to be very high, your magnesium recovery is going to increase, and it can lead to inconsistent or increased alloy addition. Your magnesium recovery can become inconsistent. Your magnesium fading rate can increase because you start boiling the magnesium for a longer time. Your nucleation fading, the rate of fading can increase, and because of all these things happen, you need to add more silicon, and because of this, you might end up in getting higher silicon because of the increase in addition rates, or you might have to control this by controlling or having a lower silicon in your base metal. So these are effects where when the pouring temperature is high, we get penetration defects in the molds, like increased metal penetration. It can lead to increased remote location shrinkage, because you're going to have the liquid metal inside the cavity for hotter for a longer time. So that means more hot spots, and then more shrinkage coming up. Reduced nodule count, because your nuclei is going to be dissolved again into the liquid metal because it is kept at a very high temperature. Your magnesium fade is high, your inoculation fading is going to be high. There will be more of gas generation from the cores, because you are going to superheat the cores, and you are going to keep the cores hotter for a longer time. The rate at which the gas generation from the core is aggravated or increased when you keep the core at a very high temperature. That means you heat the core at a very high temperature, or for a longer time at a very high temperature, gas generation is going to be more, and the rate of gas generation is going to increase, and because of it, you may end up getting gas defects. And some positive effects. Why do people go for high temperature? Is because to avoid misruns and cold labs, to avoid dross formation. How dross formation happens is, see, there are some oxides which form at high temperature. There are some oxides which form at low temperature. So all the slag forming elements, and most of the elements in a ductile iron, like iron, manganese, silicon, these are calcium. These are low melting alloys, and these elements form oxides at a very low temperature, and these oxides become very stable at low temperature. So that means you should be able to pour just above a temperature where all these oxides will not be formed. So pouring at a low temperature or having a low temperature is also dangerous, where you tend to form lot of dross, and you tend to form lot of gas defects, where you don't let enough amount of gas to be letting out of liquid metal. So low temperature is also dangerous, and very high temperature is also dangerous. So there should be a measure, and there should be control over temperature at which we tap and we pour, such that you don't end up in getting defects. So the second T is completed. So we are able to cover and study and understand about how the first T works, like the time, the most important parameter, and second, temperature, the second most important parameter. So when we are able to control all these two, do we guarantee that the casting is still going to be okay? No. There is one more part which is going to influence, even if your time and temperature is going to be correct. So we have ensured that the time taken for the graphite to come out, the time taken for the nuclei to be stable, the temperature at which nuclei is going to be stable, everything is ensured and pakka, and we have monitored and maintained it correct over different temperatures, over different pourings. What happens if there is some tricky elements which is present in your liquid metal, which has entered into your liquid metal without your knowledge, and even at their constant control over time and temperature, still leading to a defective casting. So this is what this section will be talking about, those elements and some measures being taken in foundry and how other additives can help in controlling this. So what are trace elements present in ductile iron? So these are elements which are present in very lower amounts. As you see, these elements will be in second decimal or third decimal when we analyze using spectrometer. Some are being some elements cannot be measured using like spectrometer, or which has got a less confidence or less accuracy in measurement using our conventional spectrometer available. So this is the reason why most of these elements go unnoticed, and which increases by itself and has a direct impact. Only we come to know about these elements impact after our rejections coming up. So what are the sources of these elements? So it can come from a charged material, it can come from our additives, it can come from our coating materials which we use in the process. What does these elements do? What do these elements do? These start impacting the nodularity, nodule count, and other microstructure constituents, which is going to decide your uniformity of mechanical properties. So what should we look for? What to watch for? The first thing to look into if we have a tramp element or a trace element problem is whether all the other procedures being followed are constant. So for example, there is a carbide formation suddenly you observe, and to attribute that carbide formation is because of a tramp element or trace element, we should first ensure that whether our time, temperature, other chemical composition which we can control by ourselves are already in control or not. So there are two cases. So where case one, there is a real tramp element problem. It generally comes suddenly. Say for example, there is a sudden change in the scrap material which we have bought, and there is a influx of such new scrap coming into your melting, and that goes into your production, and you get liquid metal and you pour a ductile and castings, and because of a sudden change in the raw material, it would have led to a rejection in the casting. It can be one of the case, it need not be every time, and it need not there need not be a trend in such kind of rejection. So this can be a sudden change in your process or sudden change in the raw material. So care to be taken that a traceability factor should be available, traceability procedure should be available whenever there is a change in your raw material or your process, and such changes to be monitored, and there should be control over such changes, or a full evaluation of or prediction or assessment of what is this change going to result into. So it should be there, like what ISO people call as risk assessment. So any change should have a risk assessment associated with it. So there can be case two where some elements can build up by itself. So it is in a very small amount. Say for example, titanium. Titanium comes from a liquid metal, and say for example, our pig iron has got some titanium, or steel scrap has got some titanium. So we keep using our titanium, pig iron and scrap, and our returns will also contain some titanium. When you keep adding, some trace elements keep building up, because there is very small loss available for those trace elements, where this keeps building, this keeps increasing, and over a period suddenly you will end up in very high level of trace element, and very high rejections continuously coming up. This could be because of continuous buildup. So case one is going to be sudden change, it can be one of the cases. Case two is going to be buildup. So case one and case two will have rejections, and this would have missed our overall control or overall quality checks. So care to be taken that care to be taken that the effect of individual element to be studied and understood, and it should be added to our process. So what is to be done? So every purchase of a raw material, every addition of new material into the process, or bringing up a new process to produce ductile iron with the existing raw material, we should be able to assess in all the forms, like what is its impact over microstructure, pouring, tapping, your chemical composition, your recovery rate, your fading time, your final mechanical properties required throughout the castings. So we should be having a complete understanding of any change in the raw material or any change in the process. So we should also have a thought in our mind that the effect of tramp elements on trace elements need not be its own individual effect. There can be a combination effect also. Say for example, arsenic and antimony can put together combined give you some chunky graphite or spiky graphite, or it can produce degenerate graphite. And we need not think that presence of only antimony will give you that. Even a slight arsenic, which is already available in a liquid metal, which would have been well under control or well within limit, controllable limits or acceptable limits, suddenly there is an inclusion of antimony coming into your production due to some resources. This antimony and arsenic, which is already present, combination can give you some defects. So presence of every individual elements and its effect should be understood and well thought of and being added to the liquid metal to produce good ductile iron. So these are some of the Tramp elements which is present in the ductile iron, and which is called as Tramp elements because these are generally present in second decimal and third decimals. And what are its negative impacts? And this is a broad classification. This can vary grade to grade. This can vary component to component because as we had seen, ductile iron is section sensitive slightly, and the phases, the microstructural components are formed in different sections in a different way. So the cooling rate matters, and the effect of these elements in the given cooling rate matters a lot. And say for example, titanium general acceptable limit in foundries for ductile iron should be 0.03%, and because titanium forms titanium carbides generally, and it can lead to hydrogen pinhole when aluminum is present. So here we can see a combination effect. So when titanium is present and when titanium goes high, and you already have aluminum available in your liquid metal within the controlled level, titanium plus aluminum can lead to your increased hydrogen porosity. So what happens is, to some extent, cerium additions can be done to negate titanium, or you can avoid your titanium rich scrap material or your returns material available in your liquid metal, such that your titanium levels are being controlled. Boron, again, boron in ferritic grades it has got a different control, and in paralytic grades it has got a different control. What does boron do is, boron is a carbide promoter, and sometimes it forms packs of ferrates, like remote location ferrates, and it can reduce or alter your mechanical properties. So what happens is, you can avoid boron by finding its source and then controlling it, or you can control your ferrite forming tendency due to boron by adding copper and tin, or ensuring good perlite promoting elements in a given level. Aluminium, as we know, aluminium is a nucleating element. Also, it is dangerous when added in excess. When aluminium goes beyond a limit, it can lead to more dross formation, and this dross can lead to subsequent dross formation, because when aluminum becomes alumina Al2O3, and this alumina can react with some other dross already oxide forming elements available in the liquid metal, and it can lead to a coagulative dross or coagulative oxide defects. And when aluminum is present, we know there is a tendency for aluminum can fix pure hydrogen from the moisture in the liquid metal, moisture in the mold, so it can lead to more of porosity. So control over the treatment alloys, or aluminum percent from your treatment alloys can have a control over aluminum. Tellurium, we know tellurium is a very strong carbide promoter. And where do tellurium come from? Tellurium comes from your graphite cups, where your CE meter cups have got tellurium in it, because there the chilling is done to measure the carbon content. And when these tellurium rich carbide cups, or the sample cups which is poured for CE meter check, is put back into the furnace, your tellurium keeps increasing. So, and this is done over a period, and you do not know, or you do not generally have measure for tellurium in your spectrometer, or your spectrometer might not be calibrated for tellurium. Your carbide potency because of tellurium can increase. Slowly this tellurium will keep adding in your liquid metal, which we do not know, or which we just not measure it, and over a period suddenly you will be getting carbide, and we will be worrying about it could be because of low inoculation, or it could be because of high temperature, but actually there could have been high tellurium present in it. And we don't have a general facility available readily in any foundry to analyze what kind of carbide it is. Say it's a manganese carbide, or vanadium carbide, or chromium carbide, or tellurium carbide. For us, we do a pickerel etching or nitrile etching, and we know it is carbide. So unless we know the source of the carbide, it is very difficult to classify and take the root cause. And if we do not take a right root cause, we'll be landing in different problems. So it is very essential to have a control or have a knowledge of all these elements and control over these elements. And vanadium, we know vanadium is a mild perlite promoter and is a very strong carbide promoter. And with at different grades, a different amount of vanadium is allowed. And this is again coming from your steel or your raw materials being added. And this is zirconium. Zirconium, as we know, it is a strong nucleating element. There are zirconium based inoculants available, but there is a limit for zirconium. When zirconium crosses beyond a limit, it starts providing compacted graphite ion. That means changing the morphology of the graphite in the same levels of residual magnesium and sulfur. So with same sulfur and same magnesium level, your increase in zirconium can lead to vermichloride. So that means you should not add more zirconium inoculant, or any other source of zirconium coming up should be avoided. Lead again, it leads to scattering or degenerating your graphite forms. It promotes perlite to some extent, but before promoting perlite, lead will distort your graphite which is coming up. And if it is going to be a thick section, it is much dangerous because cooling rate is very slow. When your cooling rate is very slow, by default your nodule forming capacity is reduced because there is more activity towards the carbon, and holding the carbon in the spheroid form becomes very difficult in a thick section casting. That is why your nodularity is always slightly poor in thick sections of your castings than thin sections. And if the casting is going to be very thick and very slow cooling rate, these all Tramp elements become very predominant and its effect becomes very aggressive. And next comes bismuth. Bismuth is a strong, bismuth is an element which is being added as a nucleating element, a strong new nodule count increasing element, but there is a limit. Bismuth is primarily a carbide promoter, similar to magnesium. So when bismuth goes into liquid metal uncontrolled, or when bismuth is not countered by supporting element, bismuth will give you carbides directly. The same way antimony, because antimony and bismuth are similar group elements in the periodic table. So those two elements perform in a similar way. So antimony will lead to a deleterious nodule formation. That means it can distort your nodule. It can lead to degenerated nodule. Anything away from ductile, anything away from round nodule. When these round nodules get distorted, all your mechanical properties get affected. So this again to be added in conjunction with a compatible element like cerium. Arsenic again, the same effect. So all these Tramp elements can be controlled when it goes beyond your limit, when we go beyond your acceptable or controllable limit. You can have some special additives available into your liquid metal, like elements like cerium or lanthanum, like rare earth elements, which react with all these elements and let them not react with the carbon or distort the carbon. But this is not an excuse that you can keep adding cerium or lanthanum and you can still have more amount of arsenic, lead or zirconium. It is because when these two combination elements keep increasing, it is again going to build up in your liquid metal and it can have a negative effect also. So as we say, like too much of anything is good for nothing. The same way, too much of nodulizer is not good for your ductile iron. Too much of inoculation is not good for your ductile iron. The same way, too much of trace elements, too much of cerium is not good for ductile iron. So it is to be arrested at the source itself rather than having a or taking a countermeasure. So what do rare earths do? Rare earth reacts with oxygen and sulfur. Rare earths react with grain boundary elements, which are the Tramp elements which we had discussed previously. Antimony, as arsenic, bismuth, boron, titanium, and all. It forms some compounds which does not segregate in the grain boundary, such that you don't get any grain boundary carbides. So these are some of the compounds which lanthanum and cerium and other rare earth elements can form, such that you see all these elements are formed at a very high temperature, and it does not let anything come into your liquid metal during solidification. Rare earths will help you to counter the Tramp elements present, such that it keeps a very high it forms compound which is higher than the melting point, and it has got another advantage that these compounds formed are getting converted into heterogeneous nuclei. So rare earth has got direct cerium or direct lanthanum giving you nuclei. Also, it reacts with the subversive elements and converts that into useful also. So rare earth elements has got its own advantages, also some disadvantages. So rare earths are generally being added either in the form of inoculant or in the form of nodalizer, or in both the forms, or as pure elements also. So to this we have come to the end of the presentation. To summarize, today we have discussed about how important time, temperature and Tramp elements are, and where all time is to be measured, and where all temperature is to be measured, and what are the Tramp elements generally available, and in what amount it should be accepted, and what are the countermeasures which can take, and what happens when these elements go out of range. So these are some of, or these are the three parameters which are directly in hand, which can be controlled by the foundryman directly. So magnesium or inoculant or anything provided or supplied by a different supplier, or which where the foundry doesn't have the competency or the facility available to check, um, will be notified, or will be generally tested only after the casting is made. But these three elements are already, these three factors can be directly controlled and directly measured by a foundryman. So when all these three elements have a direct control, then you can definitely have a process change, process improvement, and you can produce very good ductile iron. So variation in any of these factors, as we have discussed, greatly influence the performance or efficiency of the ductile iron treatments and pouring. And the monitoring and measuring of above parameters will have an impact in producing the casting with good quality. And when we aim at producing good quality, we should have definitely control over all these three elements and all these three factors. So with this, today's presentation comes to an end. And thank you all for listening to us, being a part of with us with this presentation. And um, and over to the audience, and now any queries can be answered.